Okay, so hello everyone, this is Akshay here, and welcome back to the another great day of our GFG POTD streak. And today we're going to cover a question of a very standard question, that is the insert a node in a binary search tree. Right, as you can see, the category is easy. So let's read a question. So given a BST and a key k, if k is not present in the BST, if k is not present in the BST, insert a new node with the value equals to k into the BST. If k is already present in the BST, do not modify. Right, so we need to take care of this case as well. If k is already present, we need to check when they do not modify the tree. Okay, तो इस क्वेश्चन को करने के दो तरीके हैं यार, बट सबसे पहले हम ड्राई रन देख लेते हैं, इनपुट आउटपुट देख लेते हैं. सो आपके पास ये ट्री है. अब बीएसटी की प्रॉपर्टी क्या होती है, राइट? यू हैव अ रूट, यू हैव अ लेफ्ट चाइल्ड, यू हैव अ राइट चाइल्ड, राइट? द प्रॉपर्टी इज कि लेफ्ट जो है वो हमेशा लेस देन रूट होगा, ठीक है, और राइट जो है वो हमेशा ग्रेटर देन रूट होगा. If any particular binary tree follows this property, then definitely that particular binary tree is a BST. Correct? Okay. So you have been given is this tree 2136. You need to insert a node 4. So where you can insert it. So clearly we will start traversing from the root. We will see, okay, that's 2, right? And now I have a key, let's say 4. तो हमारा जो की है 4 वो डेफिनेटली अपने करंट रूट से बड़ा है, तो उसकी जो प्रोबेबिलिटी होगी इंसर्ट की वो कहाँ होगी, लेफ्ट या राइट? जो हमारा रूट है वो इटसेल्फ 2 है, हमें इंसर्ट करना है 4, तो डेफिनेटली हमें राइट में मूव करना होगा इन प्रोबेबिलिटी की, विल गेट अ प्लेस. ठीक है, तो इसकी वजह से हम राइट में मूव कर गए. अब देखा मैंने कि नाउ आई गॉट अनदर करंट रूट एज 3. अगेन हमारी जो वैल्यू है वो 4 है, राइट? तो अगर मैं 3 से बड़ा कोई वैल्यू प्लेस करना है तो डेफिनेटली हम फिर से राइट में मूव करेंगे. तो मैं फिर से मूव कर गया, करेक्ट. नाउ द करंट रूट वैल्यू इज 6. नाउ नाउ विल कंपेयर. मेरे को 4 प्लेस करना था, बट नाउ माई करंट वैल्यू गिवन इज 6. तो डेफिनेटली मेरे को जो प्लेस करना है वो मेरे गिवन वैल्यूज करंट रूट वैल्यू से लेस है, तो मैं कहाँ मूव कर जाऊंगा, मैं लेफ्ट में मूव कर जाऊंगा और यहाँ पे प्लेस कर दूंगा 4. Correct? Similarly, it's 1, 2, 3 maybe. The current root value is 1 and I need to place 4, which is greater than my current root. So I'll move right. Now my current root value is 3 and I need to place 4. So definitely I have to move right again for this root node and then I can place 4 here. Correct? हमें समझ में आ रहा है कि हम कैसे वैल्यू प्लेस कर रहे हैं, ठीक है. इस चीज को करने के लिए वी हैव टू वेज. मेथड 1 इज अ रिकर्सिव अप्रोच, मेथड 2 इज इटरेटिव अप्रोच. तो रिकर्सिव अप्रोच जब लगा रहे हैं तो हमारे पास ऑक्सिलरी स्टैक का स्पेस भी कंसीडर करना पड़ेगा. इटरेटिव लगा रहे हैं तो वी डू नॉट हैव टू कंसीडर दी इटरेटिव और रिकर्सिव स्टैक स्पेस. तो यहाँ पे ओ ऑफ वन हो जाएगा, स्पेस कॉम्प्लेक्सिटी दोनों में डायवर्सिटी सेम रहेगी, ओ ऑफ एच, क्योंकि विल बी ऑलवेज मूविंग अहेड इन वन पर्टिकुलर डायरेक्शन, राइट? जब यहाँ पे आप देखें तो हम 2 से 3 आए, 3 से 6 गए, राइट? तो अगर आप देखता रहोगे तो हम एक्चुअली हाइट ऑफ द ट्री टाइम्स ट्रैवर्सल कर रहे हैं, राइट? ऐसा नहीं है कि हम पहले राइट भी जा रहे हैं, लेफ्ट भी जा रहे हैं और सिमिलरली ऐसा नोट के लिए ऐसा नहीं कर रहे हैं, राइट? हम चेक कर रहे हैं उस नोट लेफ्ट, या तो हम लेफ्ट को छोड़ देते हैं या तो हम राइट को छोड़ देते हैं, राइट? एंड इफ यू सी दैट वी आर मेकिंग द नंबर ऑफ ट्रैवर्सल्स फ्रॉम रूट टू द लीफ नोड, लेट्स से टू द लीफ नोड, एंड सो हाउ मेनी टाइम्स वी आर मूविंग अहेड, दैट इज द हाइट ऑफ द ट्री टाइम्स. ठीक है, आई होप वी आर ऑन द सेम पेज हियर. तो कैसे कर सकते हैं रिकर्सिव फंक्शन, कैसे होगा यार? Now you have understanding that how we are actually going to place the nodes in the given BST. Now please pause this video and try to think of a recursive solution, then we can proceed ahead. Correct. Let us now proceed with the recursive solution. So we will make a helper function here, let's say, जहाँ पे हम root pass करेंगे and then we will pass the value that is to be placed, that is x, right? So first we will check that if root is equals to null, that means the given tree to us is a BST, is an empty BST, right? So what we need to do, nothing. You just return. If it's an empty, then you just have to say that make a new node with the value x and just return it. Correct? Else if what we were checking, if my root value, that is root dot data, is what, say, less than key, then what we were doing, we were moving towards the left hand side, right? कि हमारा जो रूट डॉट डेटा जो है, नहीं, वी विल मूव टुवर्ड्स द राइट हैंड साइड. हमारा जो रूट डॉट डेटा है और हमें जो की प्लेस करना है वो हमारे करंट रूट से बड़ा है, तो डेफिनेटली राइट हैंड साइड में ही प्लेस करेंगे उसे. सो विल मेक अ रिकर्सिव कॉल ऑफ कि रूट डॉट राइट, अगेन कॉल दिस फंक्शन विल कॉल अगेन रूट डॉट राइट कॉमा एक्स. इन द एल्स केस यहाँ पे क्या होगा कि की जो है वो स्मॉलर देन माई करंट रूट, तो डेफिनेटली अगर की हमारा स्मॉलर करंट रूट से तो डेफिनेटली विल प्लेस इन द लेफ्ट हैंड साइड. सो आई विल से रूट dot left is equals to nothing but function of root dot left comma x. Correct? That is it. And at last, we will just say return root. Okay. तो हम इसका एक ड्राई रन देख लेते हैं यार कैसे काम कर रहा है. So let's say we have a tree like this जहाँ पे 2 1. So let me use a different. Okay, let me just draw the tree with the same color. 3 and 6, and we need to place 4, right? So we know कि place 4 कहाँ पे place होगा, यहाँ पे place होगा. But how this particular code is working, तो हमने जब एक छोटा सा recursive code लिखा है, so we should must dry run it. इसको dry run करके देखते हैं कैसा दिखता है. So what will happen? So function of 2 comma 4 will be passed first of all, right? Now what will happen? That my key that is to be need to place is itself is larger, right? So it is larger, so definitely we need to make a recursive call in the right hand side direction. So I will say 2 dot right is nothing but function of 2 dot right, which node is present, 3, function of 3 comma the key value. Now again the key that needs to be placed वो again current root node से हमारा भरा है. Then we'll again call the recursive function towards right. So 3 dot right is nothing but function of 3 dot right. 3 dot right is nothing but 6 comma 4. Now if you see that my current key is 4 and the current root node value is 6, so the key is smaller, then definitely we have to make a call towards the left hand side, right? So a final call would be made here, and what I will say that 6 dot left. So let me just shift the screen towards, yep, that will work. Yeah, so 6 dot left is nothing but the function of 6 dot left. And what is the 6 dot left is indicating in our current BST, right? It is null because you have not placed the node, so it is null, and comma 4 would be passed. Now that's what we are saying, that now we have encountered a case that after this 6 there is no BST present. So if root is equals to no null, we will return a new node with the key value given, right? So now let's just use a different color here. Okay, so this function will actually return the reference of a node 4, correct? So that is why I'm saying, I'm already saying that 6 dot left is nothing but equals to 4. So 6 dot left is equal to nothing but new node with the value 4, correct? ठीक है. So now this recursive call has been finished, right? And what was the last statement that is to be executed? Return root, right? So return root in the sense, what is the root here? 6. So it will return 6. Similarly, this recursive call, the last statement is to return root, it will return 3. Similarly, this, the root is here 2, it will return 2. And 2 would be returned, uh, uh, 2 would be returned for this entire code, right? With the updated one now, just the updated one will be that you will have 4 here in this BST, correct? I hope that makes sense. Now, please pause this video, try to code this approach in your code editor, and then we can proceed ahead. Also, let us discuss the time complexity and the space complexity again. So, what is the time complexity? You clearly saw that we are moving in either one direction, right? Either we move left, either we move right. So, definitely we are making a traversal for O of height of the tree. So, that is why I said O of height of the tree. What is the space complexity? Okay. Now you can clearly see that in the recursive stack space, what happens? This 2 comma 4, right? So first 2 comma 4 got into the recursive stack, then it calls for another recursive function that is 3 comma 4, then it calls for another recursive function that is 6 comma 4, and finally it hit the null comma 4, and then everything starts to return. First it returns and it pops out, then this pops out, and this pops out, right? So at the worst case, what was the maximum call that you were having this auxiliary stack, right? 4, 4, right? And what is the height of the tree here? The 3 in the original BST and 1 you added. So that means the 4. So that is why I'm saying the space complexity also would be O of height of the tree. Let us code this particular approach in our code editor, and then we can resume ahead with the method 2. Okay. Yep. Now it's up to you guys. Please pause this video now. Try to code the same pseudocode in the code editor, and then we can proceed ahead. Okay, great. The compilation has been passed successfully. Now let us hit the submit button. While it is submitting, let us do the constraint analysis as well. So we have used the density of O of h. And what is O of h? So the number of nodes in the BST is 10 power 5. So in BST, what is the height? What is the height of a BST? If number of nodes is given, then the height is log n, because it's a complete binary tree, because it has the 1 or 2 children, right? It can have at most 2 children. And the height of the BST in that case is log n. So if you do log of 10 power 5, right, because you're using O of h, so this log of 10 power 5 is definitely less than 10 per. That's an additional information I'm giving you here, and that is why this code is getting submitted, right? If you're not aware of this 10 per 8 logic, then definitely one video will be popping up here now, and you can see that. Okay, so it's done. Let us see the C++ code now. Okay, so that's the C++ code. It has now successfully compiled. Let us hit the submit button. Great. It has passed all the test cases. Now, Let us move ahead with the method 2, where we can see that how we can, instead of using the recursion, how we can do in space complexity O of 1. Correct? Okay. Let us use this and utilize this space here now. Okay. So what we will do here is, so let's say you have the tree again 2, 1, 3, 6, and you need to insert 4, right? So we will start from the root, we will store it in a current pointer, and we will have a parent pointer as well, which is pointing now to null, right? What this pointer is doing, that हम उस नोड का रेफरेंस निकालेंगे जहां पे हमें अपने पर्टिकुलर की को इंसर्ट करना है। जैसे की को यहाँ क्या इंसर्ट करना है, 6 में, राइट? 6 के लेफ्ट में जाएगा, तो हमारा जो पेरेंट है, जो हमारा कोड रन कर जाएगा, तो इट विल पॉइंट टू दिस पर्टिकुलर नोड, दैट इज द पेरेंट नोड ऑफ द की बेसिकली। ठीक है, तो हम यहाँ क्या करेंगे कि we will have this current. Now it will be compared that if my current root dot data, if it is lesser than my key value, right? मतलब की जो है ये बड़ा है 4 से, तो definitely हमें इसे right hand side में place करना पड़ेगा. So we will first mark it as parent and then move to its right. So this will be now new current. Now again it is 4. Again my key value is greater than my current root node. So again we will mark this as my parent, right? And I will move ahead. क्यों mark करते हैं यार parent करके, हमें पता नहीं ना कि node present है या नहीं. So that is why we are always keeping the track of the parent, right? ठीक है, तो हम यहाँ पे current आ चुका है. Now you can see you will be compared with 4 again. Now the key is smaller than my current root node value, then definitely it should be placed in the left hand side, right? So what will happen, I will again mark this as current and I will move to its left, right? So left is nothing but this is null, so I will mark, so my current will be pointing at null. So my pseudocode will look like this. So while current not equals to null, I'll keep on traversing, and what would I write ahead? I will just write that while current is not equals to null, and I will say first of all I will store the parent is equals to current, and I will check. So let me write down the complete pseudocode now. Okay, so that's the pseudocode here. Let me give you a code walkthrough now. So we were at a good point that in deciding that we need to run a while loop while current not equals to null, right? Because the current will be pointing to here at the final iteration. ठीक है, हम parent को यहाँ 6 में store करके now what we were doing, that if my current dot data was greater than x, like at this position my current dot data was greater than my key value, so definitely I made a call to left, so that's why left here, right? Now if my current dot data, let's say for this 3 and the key value was 4, so the current dot data is definitely less than key, or let's say x, then we made a call to the right hand side, that from 3 we move to 6, so that's why current equals to current dot right. Okay, now there is one other case, else return root. Now can you guys tell me that what is this case? So we have handled the greater than sign, the less than sign, so else will be handled with sign, equals to sign. So it would be handling that current dot data equals to x. So that means while we were traversing in a BST, we find that the key was already present in the BST. So in that case, we do not have to add or remove anything in a BST, and we just have to say just return the root element, and that's it. Correct? So I just say that key is already present. Okay. Okay. So the second part now. So this first part of code ensures that you have your current pointer here, the current pointer at the null, that is ensured, and you have your current pointer and your parent pointer at the node which is responsible to add the key value, जहां पे हम की वैल्यू को डालेंगे राइट या लेफ्ट में. अब राइट में डालें या लेफ्ट में डालें उसके लिए हमने एक और इफ एल्स लगाना पड़ेगा. सो दैट्स द सेकंड पार्ट ऑफ कोड कम्स. करेक्ट. तो हम चेक करेंगे सबसे पेरेंट इक्वल्स टू नल. अब ये क्या हैंडल कर रहा है गाइस? ये हैंडल कर रहा है कि ये इंश्योर कर रहा है कि ये एक एम्प्टी बीएसटी है, कि जो इनपुट में जो बीएसटी पास हुआ था दैट वाज ऑलरेडी एन एम्प्टी बीएसटी, मतलब कि ये व्हाइल लूप कभी रन ही नहीं हुआ, right? Because current was, we stored the current equals to just starting at root and parent as null. Correct? तो current root कभी चला ही नहीं क्योंकि already was equals to null था. So now that's for checking if that was an empty BST. तो हमें कुछ नहीं करना है, हमें जो new node हमने बनाया था उसको पास कर दो. तो temp हमने बनाया था, temp equals to new node x, so we return the new node, right? Now, so let's suppose that tree was not empty like in this case, and now the parent is pointing at which node? At this node, where actually the key is to be attached. तो मैं check करूंगा कि ये जो parent value है अभी, right? If it is greater than my key value, correct? Then definitely, if it is greater and I need to place a key which is smaller than this, then definitely I have to make a call in the left because that's the property of the BST. So that's why I'm writing parent dot left equals to temp. Else, that means the key value was already greater. So we need to place in the right hand side direction. So the parent dot right equals to temp. And at last, we just have to say return root, and that's it. दैट्स इट आई गेस. ठीक है. तो आपने बहुत लोग ने, मैं देखा है एक दो कमेंट लाइक यू गाइस वर सेइंग कि भाई आप जो कोड बताते हो उसका एक बार रन दिखा दो, लाइन बाय लाइन कैसे चल रहा है. तो मैं भी उससे एग्री करता हूँ यार. लाइन बाय लाइन कोड कैसे चल रहा है वही पता होना चाहिए. मैं एक बार रन दिखा दूँ तो अगर आपको वैसे ज़्यादा समझ में आ रहा है तो ठीक है, वही सही. ठीक है, तो अब इसको कोड करते हैं. एंड आई हैव शोन यू द एंटायर कोड हियर नाउ. नाउ प्लीज पॉज दिस वीडियो हियर एंड ट्राई टू कोड दिस अप्रोच इन अ कोड एडिटर एंड देन वी कैन रिज्यूम अहेड. Okay, so that is the same pseudocode written in Java here. Now let us hit the submit button. Again, what is the time and space complexity that we were deciding to move either in left or right, and how many traversals we are making exactly to the height of the BST. So that's why O of height of the BST is the time complexity, and the space complexity, we're not using any recursive stack space, any other data structure space. We are making just some new pointers, that is temp and current. So that is O of 1, right? Let us now look at the C++ code. Great. So that's the C++ code. Let us hit the submit button for this code as well. And then we can quickly summarize all the approaches we have seen, and then we can end this video. Definitely. So great. Everything has passed. So let us now resume ahead with the summary. So what are all the approaches we saw here? We saw that we need to do an insert in the BST, and I have showed you that how actually we need to do, because it's the BST holds a special property that the left is less than the root and the right is greater than the root, correct? So we discussed two approaches here. The first approach among them being is the recursive one. तो ट्री की बात हो रिकर्जन ना आए तो यार मजा ही नहीं आएगा. कुछ अधूरा सा लगे. तो recursive में we have seen, since we are using the recursion, then definitely there would be attached an auxiliary recursive stack space. So that's why O of H has time complexity and O of H has space complexity. But we saw कि हमने recursive stack का space जरूरत ही नहीं है. Since we are making a call to right and left, and we are just making we are just tracking the parent pointer जहाँ पे हम अपना key attach करेंगे, right? तो recursive stack की क्या जरूरत है वहाँ पे? So we just tried an iterative approach. We just moved either in the right hand side to the or in the left hand side according to the values greater than or less than the root, current root. So that's why the time complexity is O of H and the space complexity is O of 1. Now, on this good note, let us end this video and let us meet again in the tomorrow streak of 318. And yes, till then, keep learning, keep growing. Bye bye, and take care, guys.